Hello and welcome to the first session of our Formula Student FEA workshop, organized by SimScale in collaboration with Formula Student Germany. Yes, I'm happy to see that so many people have joined today for our very first session about our brand new online workshop, FEA for Formula Students and FEA. And for those of you who joined one of our workshops in the past, you may already know the procedure. Before we actually start to dive into our today's topic, I would like to make sure that you can hear me loud and clearly. And we're using a software called GoToWebinar to deliver the live stream of the session to you. And right now, you will, depending on the device you use to listen to this webinar, you will find the so-called GoToWebinar control panel in front of your desktop. And there is a button called Raise Your Hand. And in the case you can hear me loud and clearly, please click the Raise Your Hand button to show me that everything is working fine. Great, I already see a lot of hands and also some names I can remember from our last workshop in September about CFD, like Don, for example, or Dominic or Alejandro. It's great to see you all here. And since everything is working from a technical perspective, I think we can start. Just one last thing. We also offer alternative to listen to the voice of the presenter. And in the case you maybe don't have a good headset or your internet connection is poor, you can also use our toll-free audio service numbers. Therefore, just choose the corresponding number from the table you can see right now on your screen, and enter the access code 361059726 once you're asked. First of all, I would like to introduce myself. My name is Milad, and I'm working as a product marketing manager at SimScale. Some of you might know me already from the past webinars, and let me just tell you some things about myself. So I've started more than 10 years ago to work with engineering simulation. And basically, I was in a quite similar situation like you are today. Back then, I was 14 years old. I was still going to high school. And I was very interested in F1 cars, and especially in aerodynamics. And I wanted to understand how aerodynamics of professional or modern race cars are working. And back then and today, wind tunnel test is very expensive. So I had the idea, why don't I use simulation? And I'm telling you this because I can really understand how you sometimes struggle and all the pain when it comes to learn engineering simulation. And I know that it can be very frustrating sometimes, and it looks very complex on the first view. But in the end of the day, it can really help you to become a better engineer. And not only because you can now use more modern tools and better tools to improve your designs, but also because it forces you to understand what you're doing. And yes, in the past 10 years, or mainly in the past 7 years, I started also to work as a consultant. And during that time, I worked also as a CFD engineer in Formula One and in the World Rally Championship. And yes, I'm very enlightened to share all my knowledge with you. And yes, today we want to start our journey through the world of FEA. And yes, maybe just some organizational things. This workshop is made out of 2 sessions. The first session, which is today, will focus on the very basic fundamentals of FEA. So we will learn like how is FEA working, what is the idea of FEA. We will talk also about the different steps. So how do you prepare a simulation? And then we will focus, let's say, on the hands-on aspect of our today's session, which is setting up our very first own structural finite element analyzers. And yes, finally, we've again prepared a homework assignment for you. And for those of you who don't know what that means, this workshop basically has is made of 2 components. One component is a live webinar which you can join. And for every live webinar, we also provide you with a corresponding and voluntary homework assignment, which is about setting up the simulation on your own. And all participants who submit both homework assignments will get a certificate. But we will talk about this organizational things in just a few minutes. So first of all, and just to make it very short, but what is this workshop about? We started to talk with former student Germany like 1 year ago and asked them if there was anything we can help. And during this discussion, it came out that a lot of teams are struggling with using engineering simulation and integrating it into the CAD development process. And we think that there are a lot of reasons why smart students who are able to build a whole race car are sometimes struggling when it comes to learn FEA or CFD. And the idea is that this course should combine the best of both worlds. It's very hands-on on the one hand, on the one side, we are using real FSAE teams, CAD data, real load cases, and try really to put you into the seat of those engineers. And on the other hand, we also think that theory is not everything, but at least everyone who uses FEA or simulation in general should really have a rough understanding of the most important fundamental. And that's what this workshop is about. So we want to show you how to create precise simulation of your own car design, which can help you to improve your car. We want to show you how to utilize the results from the simulations and how to translate them into design decisions. And in the end of the day, our final aim is that after taking part of this workshop, you are able to develop and improve your FEA methodology on your own. And as I mentioned, our workshop is basically made out of 2 parts. We have a live webinar, and every live webinar comes with a corresponding homework assignment. And as I mentioned, there is no prior knowledge or software or hardware required to join this workshop series. The only thing you need is motivation and, time and passion. Regarding the homework assignments, you can share the homework assignment with us using a form on simscale.com, and everyone who submits both homework assignments will get a certification. And I will show you this process at the end of our today's sessions. And finally, I would like just to answer some questions which are asked very frequently. The first question which is asked every time during a webinar is, will this workshop be recorded? And yes, we will record this workshop. We will also record the next session and send you a link to the recording within the next days. And in the case you can't wait to start to do your own simulation, we recommend to wait until the end of the webinar, because during the webinar, it's really the best opportunity to ask questions and stuff like that. And after the webinar, you have more than 1 week to work on the homework assignment. And in the case you need support, don't worry. We will support all participants, independent if they have questions regarding theory or if they need help with a homework assignment. And therefore, we have created a dedicated section in our SimScale forum where our engineers will instantly help you with every problem you have. Okay, all right. Last but not least, I would just quickly like to introduce what SimScale is doing and what we are working on. So SimScale was founded 5 years ago as a spin-off of the Technical University of Munich. And back then, the vision of the founders was to enable every engineer and designer in the world to access engineering simulation, which is not possible with traditional tools so far because they are very expensive. You need to invest like 20,000-30,000 euros just for the license and hardware upfront, and also because of missing knowledge, flexibility. And so we created SimScale, which is a 100% web and cloud-based simulation platform, which means you only need a standard web browser with an internet connection to access our 3D simulation platform. There is no installation, no need of your own, no usage of your own hardware, so all calculations, which can take a lot of time, will be computed in the cloud. And we provide, and our platform is also free for use. We have a freemium pricing model, and for all formal student teams, we offer free sponsorship. And during this course, you can use our platform as much as you want. And in the case you want to get free access to a professional account, which allows you to create private projects too, just reach out to us and we will sponsor your team. And the great thing about SimScale is it's bringing together the functionality, so the workflow in your web browser, the content. We have hundreds and thousands of public, accessible, reusable simulation setups you can directly import to your workspace, and we are connecting the people. SimScale is the largest space where engineers, designers, and simulation expert meets. All right, and since I already mentioned that you can get sponsored by SimScale, let me just put it into the nutshell. So we're offering sponsorship for every teams for participating at Formula Student, or Formula SAE, or similar competition. And basically, there are not a lot of requirements. The only thing is that you need to be in an official team, and it's very easy. You just need to go on simscale.com/student competitions. And there you can find for the three largest FSA or Formula Student competitions on subpage. And let's say you're participating in Formula Student Germany. Here you will find all the information. And here you can apply for the sponsorship by just filling out this form and sending it to academic@simscale.com. And the sponsorship comes with a lot of advantages. So first of all, you get a team account with unlimited computing hours and private projects. You get private premium SimScale provide via chat, which is also restricted usually only to our professional and commercial customers. And maybe the most important things, you get access to exclusive content, webinars, and tools. This week, I think yesterday, we just had our very first exclusive webinar for this quarter with René Hilhorst, former head of aerodynamics at Toyota Formula One, who introduced our students to his 2D wing optimization tool, OptiProf, which all our sponsor teams get also for free, and for sure you get access to all our professional trainings for free. All right, so I think we've talked enough about administrational stuff and organizational stuff, and so let's get started with our journey through the world of FEA right now. And also, one thing, in the case you have questions, we have a Q&A at the end of the session, but please feel free to submit your question all the time through our questions toolbox. And my colleague Anna, who is our academic program manager, is also with us at the session, and she will answer your questions in the chat. And in the case they are relevant to a larger audience, we will for sure discuss them during the Q&A. All right, so what is FEA? And basically, FEA stands for Finite Element Analysis, which is maybe a weird word for you. But the meaning of FEA is basically that it's a kind of summarizing virtual experiments which allow you to predict, let's say, how your real object will react to forces, vibrations, heat, etc., based on a computational or based on a computer. And the great thing is that it's basically a virtual lab that we can utilize all the time to test thousands or hundreds or thousand different design concepts in a very early stage. And one thing which I think is confusing most of you is actually the term finite element analysis, because the term comes from the world of math, and it's basically FEA is describing a methodology to solve partial differential equations. You know, this kind of weird equations which you basically cannot solve in most of cases, and not solve them analytically, and that's why it's called FEA. But basically, FEA, you could also call it structural simulation. And on the slide, you can just see three very different examples of how FEA can be applied. And again, to put it in a nutshell, FEA is about virtual experiments on your computer, which deal with a reaction of real-world solid objects to forces, vibration, heats, and other kinds of loads. And on the left side, for example, you can see structural simulation of aircraft engine bearings, which are used to connect the jet engine of the aircraft with the wings. And here you can see three different design variants. And for all of them, we use the same load case. So a load is applied. Let me show it to you. A load is applied here and here and here, and there our part is fixed. And then we calculate the stress, and this colors are representing the stress. So red means a high stress and blue is a very low stress. But we are not only limited, let's say, to this kind of static or loads. We can also do like we can also have like vibrations as a load. Here, for example, a very, let's say, prominent example. This is a bridge, and this simulation is representing, let's say, the vibration and eigenmodes of this bridge. And I'm quite sure you know this very famous video. It was showed to me several times at university, where a group of soldiers is walking over a bridge, and since they are like walking in exactly the same rhythm, the bridge starts to collapse. And yes, but it's, as I mentioned, it's not only limited to mechanical loads. You can also have, like in this example, heat loads, etc. And basically, what FEA is doing is it's transforming a continuous real world problem into a discretized numerical problem. And what does it mean? Well, let's start with a very easy example you should remember from university. Let's say this gray thing is a very short bar, or let's call it a cube from metal. And it's fixed on the side. So do I also have a pen? No, I need to use this pen. So it's fixed on this side, and I'm applying no here load, a force. And this force is changing the length of the metal bar. And this is a very, very simple exercise. I'm quite sure you had something similar at university during your introduction to strength analysis or technical mechanics. And if we think about this example, or about, for example, linear spring, which is also a very good example to get introduced to FEA, we basically have a relationship between our stress sigma here, my elongation, epsilon, and my E modulus. And if you think about, for example, a spring, you would not talk about stress, but you would have the elongation and the stiffness. And basically what we're doing, we have a relation between an external force, how this force changes, let's say, the shape of the material, and how this will change internal forces and stresses inside the material. And if we think about this easy examples, it's very easy to understand what is the idea. And now let's say we have a more complex problem, like this hook, which has a very complex shape. And here it's not so easy to apply these very fundamental equations, but we can do something else. We can like divide our model into a lot of small sub-elements which have these regular simple shapes. And that's what I referred to when I said we're transferring continuous domain to discretized domain, because here we have a continuous domain. And if we are, and continuous means that we have basically an infinite number of points. Since we have the, it's like the infinite resolution of real world objects. But this is something we cannot solve with a computer. So what do? We replace this problem by a simplified problem, which is assembled by these simple geometrical shapes, which we call elements. And basically every of these elements, it's representing an infinite piece of material. And the nodes, which are at the corners of this element, they are connecting everything together. And that is basically the idea of FEA, and therefore divide and conquer is maybe a thing you should remember, which will help you a lot of times to remember on the basic fundamentals of FEA. And just a general thing, because I can imagine some of you have maybe already attended some courses at universities about finite element analysis, and I know that this was a quite simplified explanation. But as I mentioned, Our aim is to get started first of all. And in the case you want to learn more about the fundamentals and the theory, we have a lot of other good resources you should take a look at, like our free FEA masterclass workshop, which you will also find on simscale.com/webinars and workshops. But let's talk again about this simplified shape. So basically, it's possible to do FEA in 1D, 2D, and 3D. And depending on which dimension I want to take a look at my problem, I have different kind of elements. So for 1D, I use beam elements, and basically they are one-dimensional. For 2D, I can use triangles as well as quads. And again, I have several options. So I can use the 3-noded quads or 6-noded quads. And if you think about it, using more nodes on one edge, what will it change? It will just like change the resolution inside this element. So we will be able to interpolate with a higher order and a higher resolution between these nodes. Because actually, what the computer later is doing is only calculating what is happening at the nodes. And if we talk about 3D, we have some more possibilities for elements. And just to make it quick, on SimScale, basically, we support this kind of elements. Why this is called first order. And this is second order. And one thing which is very important when you think about these elements and how they should be distributed and sized. In the end of the day, you are just calculating the solution for every node, which means in between the nodes, your simulation will don't give you any values. So you need to interpolate between. And if you use the second order elements, your elements are larger, which means it will take more computational resource to compute, but the interpolation is better. And here we have between the nodes a linear interpolation, where we have a quadratic interpolation here. And especially if we have larger changes of stress or strain, sometimes it's smarter to use these elements, because here I have a higher resolution at the same size compared to the first order elements. Let's see if we have some questions so far. No questions so far. Seems like you can follow me quite good this time. Perfect. Now let me erase my pen again. And okay, very important point is material modeling inside this FEA simulations. And if you think about, we have the 3 components, right? The material modeling is and in the end of the day, what was our stiffness at a simple example of a spring. And basically, and this is very important side information you should maybe keep in mind, this stiffness is basically applied on these lines. So we need the stiffness to, you can also imagine, if you want to have a mechanical explanation, you can just imagine the edges of the elements as being the direction of springs fastening the model together. And when it comes to material modeling, you have a lot of different options. And on SimScale, the great thing is we have a material library where you can easily import materials and easily describe materials on your own based on the standard mechanical properties. And here an example for steel. And for linear simulation, for linear elastic material behavior, we just need to say if it's isotropic or not. So it's applying in all directions the properties we're defining now, and the Young's modulus, and we need the Poisson's ratio. And the great thing is, these are all informations which are widely available for basically all materials. And I'm quite sure you had this tangential test, or you heard about it at university during a course. And you get this stress strain diagram, and out of this diagram you can basically take all the information you need for modeling the material. So if you want to model linear elastic behavior, you just need the Young's modulus, which is rise divided by run, so it's the slope of this graph here of this linear part. You need the Poisson's ratio, which is in the end like connecting elongation in or let's say the change or the deformation of your element in all three directions, because if you think about it, if you increase the length of something and the volume is not changing, the cross-section has to change. And this is described by the Poisson's ratio, and you need to add the density. And if you have plastic, if you want to investigate plastic material behavior, it's a little bit different. You still need the Young's modulus and the Poisson's ratio to describe what is happening in the linear part of, or let's say in the at the beginning of your simulation, because most of the time it's linear material behavior at the beginning. And this plastic behavior, there you just need to provide this stress strain curve as a CSV file with some coordinates. Let's talk about some other quite important aspects of FEA. Especially, one of the things are so-called boundary conditions. These boundary conditions are describing how your model is interacting with the surrounding world. And if you think again about our spring example, if the material, or if our material modeling is like the stiffness, then the loads are the external forces. And there are two kinds of boundary conditions. We have constraints, and constraints are like boundary conditions that restrict the displacement of the nodes in the mesh, which means if I add, for example, on these elements here, constraint boundary condition, they won't move anymore. And let's say the opposite are load boundary condition, which are adding pressures of forces in the end, it's forces to the nodes, faces, or even to a whole volume. And in the end, you need loads as well as constraints to have a simulation, because without constraints, your simulation will crash, because most of the time it's you need nothing will happen, because the model will just translate or move through your world, but there won't be any mechanical change. And without the loads, most of the time nothing will happen. Great. And finally, if you've prepared run your simulation, and we're talking now about the structural simulations, you can investigate stress, strain, and displacement inside your whole model. All right, I see some hands were raised. Guys, do you have questions, or is there any problem with the audio? Oh, not at all. Everything seems to work. In the case you have a question, just write it into the question toolbox. Okay, all right. A question I'm asked a lot of times is, what about my results? Are they correct? And the true answer is no, your FEA simulation results will never be correct. And I hope this will not shock you, but if you think about it, it really makes sense, because what we do when we run a simulation, or what engineers basically do all the time, is trying to describe or to create a model which is describing the real world. And all the time we know this is not necessarily the real world. And if you think about it, if you really want to have an absolute answer, FEA simulation results will never be 100% correct. But most of the times they are so correct that the accuracy is enough, and compared to other analysis types like structural simulations or testings, they are much cheaper and much easier to perform. Well, we already have some questions, and I knew that this question will come up, Sashini and Mialio, and I hope you are not mad about me if I answer them during the Q&A or just in 10 or 15 minutes. So, and regarding your results, so if you do engineering calculations, or if you have a project, you should do calculations every time to make sure that you are correct with your assumptions, stuff like that. And one option to make sure your results are correct is to do physical testing to validate what you've done. But these questions will right now might be helping to answer if it's right or wrong, but now how you can impact that. And basically, yes, you have to avoid what we call errors. And an error doesn't necessarily mean that you did something wrong, but maybe it means that you chosen the wrong model, or the tool is not really suitable for your problem. So the very first thing which can happen is a modeling error, which means in all the cases we are not analyzing the real physical model, we are analyzing a simplified mathematical model. And this is basically a great source for mistakes and problems, because the simplest example is you assume something to be linear, but in reality, it's a plastic deformation. And then even if your simulation, from let's say from the handcraft perspective, is 100% correct, if you used like a wrong approach, your simulation will be wrong. The next kind of error which happen a lot of time are so-called discretization errors, which means that your accuracy of the results for sure depends on your mesh and on the size of these elements, because you're only calculating, as I mentioned, for every node the result, which means you need smaller and more elements where you expect to have high changes like high stresses, high strains, and you need a more coarse mesh in the areas where you expect to have lower stresses. And there is no wrong or right. Basically, it's a trade-off all the time. The perfect FEA model is as coarse as let's say as fine as necessary and as coarse as possible. And also something you should keep in mind, even if we would have the perfect discretization, you should not forget that all these equations are solved numerically. In the end of the day, what happens is that we got the mesh, our loads are put together, and so we have our mesh, we have our stiffness, and for every node, and we have our loads. And this is put together to a large LGS, a large matrix with up to like 100,000 or 10,000 of rows. And this equation system is solved numerically, which means in any case, you will never have a 100% correct solution. And your responsibility as a user is to really make sure that you understand the problem and that your assumptions are right and you really follow the right procedure to set up the simulation, because it's very easy to create a smooth and colorful picture with nice stress distributions or something like that. But this can be produced by any model or any tool, independent if it's good or bad. And actually, you can even create them with Photoshop. This is also something which I saw during my career, like engineering departments who had like simulation tool, but not able to use it and just like it was like Photoshop, like tuning the results. And that's not what simulation engineering is about. So your responsibility is to make sure you're using the tools the right way. And now let's take a look at structural analysis types at SimScale. So when we talk about structural simulation, I mean all the simulations which are dealing only with displacement, forces, and stress, and not with heat and heat transfer. This is something we'll focus on next week. And basically, you have three different, let's say, paths you can choose, or simulation types. First of all, you can choose if you want to do a linear, nonlinear, or dynamic. So as I mentioned, linear means that the relationship between your force and your displacement is linear. And it also means in some cases, or as a consequence also means, that your material behavior remains in the elastic zone. You will not have any permanent or plastic deformation, and therefore simulations are only valid for small deflection and rotations. And a very good example is, if you think about this, is if you want to do a simulation, let's say, of your, let's say, a mechanical part like a suspension arm. There, you want it to stay linear, because once it leaves this linear zone, this elastic zone, you will have plastic and deformations, and the material will start to crack and fail. And in the case, in this plastic area, I mean, even if the results are good, you're lost anyways. The opposite is the case if you think, for example, about your crash box simulation. And your crash box is only used one time, and its job is like to convert as much kinetic energy as possible. And with nonlinear, we mean that the relationship between force and displacement is nonlinear, as well as we have nonlinear geometrical changes. And the material yields or has other material non-linearities. And as a consequence, also it means that we can apply it, or we need to use this when we have very large deflections and rotations. And now I think you got what is the difference between linear and nonlinear, but this is just one of the dimensions. The other dimension is if it's static or dynamic. And static basically means that your load is added very slowly to your model, and you can therefore ignore inertial forces and damping. Basically, there is nothing static in the world. Everything is dynamic, but as long as it's slow enough, we can assume it to be static. It's one of the things, the most common assumptions in engineering. And if we do a static simulation, therefore, there is no physical time, which means, let's say I have a bar and I'm applying a rising load. And as long as I'm adding this load very slow, it makes not a difference if I add it like increasing the load, double the load every 10 minutes, every 10 hours. And in contrast to that, dynamic simulations, there we really have a physical time, which means we have no limitations. Loads can be dynamic, they can be a function as a time or a function of frequency, and can be added very rapidly. Very good examples are shocks, vibration, and seismic loading, where the load amplitude varies significantly with respect to time, and where I really need dynamic simulation because these dynamic effects also will change the physics. And it's more complicated and more realistic, as mentioned, than static analysis. And as I said, basically static is just a very simplified special case of a dynamic simulation, but every time you should go with a simpler version. So if it's possible, go with linear instead of nonlinear, and if it's possible, go with static instead of dynamic. And yes, I hope that this graph is a little bit bringing light into this issue. So this is one way to like structure different analysis types, but you could also like start to separate between static or dynamic instead of linear or nonlinear. It's up to you. Great. Now let's take a look at our today's example. And again, we've prepared a very hands-on tutorial for you. And today we will talk about something which I think is relevant for every team, independent if they're using or if they're building an autonomous vehicle, an electric-driven vehicle, or a combustion race car. We will today investigate such an upright. And just to summarize it, for our FEA simulation, we need three different types of input. We need, first of all, the geometry, which is our CAD model. We need the material properties, which is based on library and database, and the mesh we create, and we need load. And to get the load, that's most of the time the very first big problem. Because usually, and I really did a lot of trainings in the past 2 years, once people really got the first idea of FEA, the first thing they start to struggle with is, okay, how do I get my loads right now? And now let's together set up the simulation, or take a look at least at the setup, and try to understand what is the workflow, what decisions you need to take during this process, and how this is related to race car design. So the very first thing is to prepare the CAD model. And on the left side, you can see the CAD model, for example. And there are three things you have to do basically. First of all, which can be summarized as cleaning up your CAD geometry. So what means cleaning up? Well, let me give you another example. Think about an airplane. Airplane has a lot of screws which are connecting everything. I would guess millions of screws. And if you think about all the screws, do you think they have an overall impact on the total structure of the model? No, I also don't think so. But if I would like to consider them into my simulation model, it would blow it up. So the difference between a model with all the screws and without no screws is very small in terms of result accuracy and result outcome, but the difference between them in terms of computational effort is gigantic. And therefore, we need to simplify our model. And again, as simple as possible, as detailed as necessary. And if you think about this upright, the CAD, you will have a kind of, let's say, production CAD model used on a CAD system, also later to create technical drawings and let's say CNC code for milling the upright. And this upright has a lot of details you don't need for your simulation. So the first step is to simplify the model as much as possible, which includes, or basically there are three strategies which can also be combined. One is defeature the model, which means you take your existing complex assembly, which like say hundreds of different parts, and you remove all unnecessary parts and design features like holes which are not needed and edges which are not needed until your model is as simple as you want it. Another strategy, which is often used together with defeaturing, is using Boolean operations, which mean you merge several parts of an assembly which have no physical interaction with each other to one part. And the third option is called direct modeling, which means that you, and sometimes this is really smarter, that instead, for example, of investing hours and days in cleaning up existing complex CAD model, you just rebuild it from scratch, a very simplified, easy model. And the next step is to find out about your load path. So which loads are acting on my upright? And this depends for sure in your case. But especially for FEA, I think you should really talk to your vehicle dynamic colleagues at your team. And they should be able to provide you with loads. So you can also start with very easy free load diagrams, but usually it's quite simple. And here it's very simple because the team which provided us with this CAD data already had the vehicle dynamic models and were able to provide us with all the loads which are occurring inside or through the suspension arms. And in this case, we can imagine that we have a fixation on the wheel hub. Don't forget, in physics, we can consider things to be relative. So sometimes there are several options to model something, but we decided to fix it at the wheel hub, and then we'll add several loads. So one load is coming from this wishbone here. The other load is coming from your steering axis. This load is from the lower wishbone, and this one load is from the other lower wishbone. And now I will show you how to set up the simulation or how such a project can look like. Just one thing, a lot of people said that they have to leave right now on the next couple of minutes, and don't worry, we will record this. As I mentioned, we are recording this webinar, and we'll send you the recording. And now let's take a look at our live demo. And therefore, I will, switch to the web browser. Just 1 second. And this is, by the way, this is SimScale, so everything is happening here in the web browser. I've logged in with my account, and now I'm accessing our public project database, which is a library of 100,000 public simulation projects, which you can import, including everything you need. And if I look, for example, FSAE upright, I can directly find a project. This one was created by Jim Sean, who was one of our consulting partners, a really experienced engineer, who is also, I think, judge at Formula SAE Michigan. And now let's take a look at Jim's project. And so, the very first thing he had to do was uploading the CAD model. And this is the CAD model, and as you can see, it's very important to make sure that the CAD model is watertight. And yes, and the next step, he created a mesh. And as I mentioned, meshing is about dividing your model into these different parts. And at SimScale, we have a lot of different meshing options. And for FEA, we just support these tetrahedral elements. And yeah, we can do it completely automatic. You can also do it based on all your own settings. So he just choose like which geometry he wants to mesh. Then he added this mesh operation, tab dominant, and said automatic mesh sizing. He wants a mesh fine mesh. First order, it wants to use 4 computing cores. And then it took like about 50 minutes to generate the mesh. You can access the log. And this is how the final mesh is looking like. And as you see, SimScale is quite smart. So the mesh was automatically defined in those areas where we have sharp edges and where we expect to have high loads. And we can also take a look at the mesh. So we can clip it, for example. No, let's move this plane in X direction a little bit, like let's say 1 meter. It's too much. 0.7, 0.8. Oh, looks 0.75. Click on apply. And then we can even take a look inside the mesh. It can take some seconds. Right. Why? It seems like my Wi-Fi is a little bit of struggling. I'm sorry. Maybe let's do first of all a quick wrap up. Sorry, guys, it happens every time I have a webinar. I have no idea why. It's real. I think it's related to the fact that internet connection is too slow right now. But once you've created the mesh, you can switch to the simulation designer and actually set up the simulation. And this is really straightforward. So first of all, you have to choose which simulation type you want to do. And in this case, static. Then you have to add the mesh, choose the mesh you want to use. In this case, the mesh we already had. Then, as I mentioned, you can just add a material, in our case, aluminium, and then you just need to add constraints and loads. So our constraint in this case is here. Let me change the representation. So here our model is fixed. It cannot move in any direction. And here we have our loads. Load 1 is acting here. Load 2 is acting here below. And load 3 is our actual brake torque, which is then applied to the upright. Yes, and then finally you just need to choose a number of cores and start the simulation one. And this one took 4 minutes. And once this is done, you can just go to the post processor and evaluate your results in 3D. And this is just simplified. You can also add some other interesting items like add automatic calculations of maximum and average stress and stuff like that. Yes, and this is the result of the simulation. It's loading right now. And until it's loading, let's just wrap up what we've discussed in the meantime. So Right, now I'm back, sorry. So the first step is creating a mesh, and there you just need to create a new project, choose TED-real automatic meshing. We choose mesh of first order since we don't expect to have large deformations, and start the meshing project. And two things you have to do before, or which are advanced topics we want to discuss today, which is more for my intermediate users, is how to do CAD cleaning and repair. By the way, we talked about that a lot during the Formula SAE CFD workshop, which you can also find for free on simscale.com. And for sure, you can also do manual meshing in theory. The next step was to do the simulation setup, which means we had to choose, first of all, which kind of analysis we want to run. We assigned the mesh. If you want, you can also group surfaces and stuff like that to create the topological entity sets if you want. And then we define the material and the two kind of boundary conditions, our constraints for the wheel or the constraint for the wheel hub and the loads for the control arms and the brake torque. And then you just need to start the simulation. And finally, you can do the result evaluation in the web browser. And this is what we want to try right now. Yes. Okay, sorry, guys. Usually it's really quick, but my computer is struggling with especially mentioned connection with running GoToWebinar, Google Slides, and SimScale in parallel. And this is the result of our simulation, and this is representing the stress. And we can also take a look, for example, at displacement if we want of different other stress types. We can also change the scale of the color legend, do snapshots, basically whatever we want. Now this is the displacement you can see. So we have here the highest displacement and basically no displacement here. And yes, you can do a lot of other stuff, but we will show you this in detail in the step-by-step tutorial for the homework since we're running out of time. All right, and yes, as I mentioned, you can visualize displacement. You can calculate maximum stresses inside the volume or for defined points, and for sure there's a lot of more stuff you can do. Yes, now I would like to introduce you to your homework assignment for this week. And actually your homework is to perform the simulation I showed you on your own. And therefore we have prepared a step-by-step tutorial, which you can find here. It's not public, but my colleague Anna will put it public in a couple of minutes, I think. And on our forum, on the SimScale workshop, there is a dedicated section FEA for Formula Student FSAE 2017, and here you will find later the recording, a link to the form to submit your homework, as well as a detailed description of the aim of the homework example and how to set it up. And you have 1 week after send out the recording, the email with recording and the link to the homework assignment to submit your homework. All right, and now it's time for the Q&A, and we already have some questions. So the first question is by Sachin, and he wants to know how to calculate angular displacement in a torsion test. Sachin, can you maybe describe your question more in detail? Because you can, without any problem, add torsion loads and torsion, or let's say rotational restrictions to boundary conditions. And if you describe it a little bit more precisely, maybe I can just show you how to do it right now. Sachin also wants to know how much of safety factor we should keep. And that's a good question. It depends on the application, your model, and the material. And for sure, in racing, you are using much lower safety factors in the real world. But for example, what I would suggest at least is to have a safety factor of between 2 and 4 at least. Right, let's see. Then Akash wants to know, how do we consider fatigue loading in FEA? Well, that's a very good question, and there are a lot of different approaches. And the approach we are following on SimScale is that you basically there is some formulas and some processes how to translate, let's say, a static or dynamic simulation result into a fatigue result. And it's like you calculate a replacement load. This is what you're interested in, please reach out to us. And because we're right now preparing for next year our curriculum of workshops. Okay, Navas wants to know the difference between triangular and quad elements, which are used for what when doing discretization. Well, TED elements and quad elements are how you use them depends on your application. At SimScale, as I mentioned, we only support so far TED elements for FEA, and generally speaking, quad elements are easier to solve because you have less, let's say, edges, but the same time of nodes. But TED elements are much more flexible. Shatan wants to know how we can understand his mesh quality, since other tools are have giving various parameters. And we have something similar at SimScale. In this meshing log, you will find there is like detailed description of your mesh quality criterion. We will get the automatic warning in the case your mesh quality is not good enough. All right, let me see how many questions we have, which are not answered so far. And then some people want to know if we also support non-isotropic materials. So far, we're not supporting this material, but it's definitely in our roadmap, and our development team is working on it. So right now, you cannot simulate composite materials with SimScale, but I'm quite sure this will be possible soon in the future. All right, I think we covered most of the questions. Unfortunately, our time is over, but we will take those questions which were not answered so far and answer them into a blog post. Thank you very much for your time. I hope to see you next week, and where you will learn much more about details, and we will focus on heat transfer simulation. Thank you very much for being here with us. Have a nice week. See you next week. Bye.